pleasure to introduce you Oleg Lisovyi, who's going to talk about logarithmic Painlevé functions and Mathieu stability chart. Please.
Thank you very much. Thank you, Alessandra and Giulio, for organizing this nice workshop and giving me the opportunity to talk about this project. So this is actually a work in progress that has been continued for some time already with Pavlo Gavrilenko, who is here, and Misha Bernstein, who is not here, but who is familiar to many of you. So before I start, maybe it will be useful to say some generalities to make some snapshot of the talk. So it is, we are going to be interested in the problem of reconstruction of linear differential equations from their monodromy. And this gives rise to two kinds of special functions. So one type of special function is Mathieu accessory parameter. And it is known since the mid-80s, basically, that these kind of functions are related to C equal to infinity or quasi-classical Virasoro conformal blocks. Now, in the gauge theory language, this corresponds to Nekrasov-Shatashvili limit. On the other hand, we will also deal with the functions with solutions of Painlevé equations, particularly with solutions of the so-called Painlevé 3, the most degenerate one. So these functions are known to be related to C equal to 1 conformal blocks, which in terms of gauge theory corresponds to self-dual case epsilon 1 plus epsilon 2 equal to 0.
So you mean Painlevé 3D8?
Yes.
Conformal block, but this we take.
Yeah, irregular conformal blocks. Actually, I have chosen to speak about this most degenerate situation because just for notational convenience, all of this actually has a lift to other equations. Right. So actually, what was known in the 80s, of course, was of course not the irregular quasi-classical conformal block, but the usual one. Right. And there is a relation between these two kinds of functions.
Sorry, Oleg, but also the usual one still is related to Mathieu or?
No, to Hoyne.
Ah, okay.
So it is Hoyne equation. So there is a well-known classical relation, which, for example, in the Hoyne case goes back to maybe in 1905 or so. So basically, Mathieu equation is related to special points of Painlevé functions. And on the conformal theory side, this corresponds to the so-called blow-up equations or quasi-classical limit of blow-up equations. So this is the picture, and it is important to note that all of this is very well understood by now for generic monodromy. Generic means, well, semi-simple in the sense that I will explain later. And so what we are going to study, what we are going to try to understand is the case of pathological non-semi-simple monodromy. So what happens on the Mathieu side, what happens with Painlevé 3, and so on. Right. What is the motivation? Well, there are two kinds of motivation concerning, for example, these Painlevé equations. So first of all, this solutions corresponding to non-generic monodromy, they appear quite often in applications, like in the Ising field theory, in the computations of entanglement entropy, but also simply because we want to describe all of the solutions of this So this relations gives you basically a generic two-parameter family of solutions, but we know that these are not all solutions. There are also two extra one-parameter families with somewhat pathological asymptotic. So this is the kind of things that I'm going to talk about. But let me start with Mathieu equation. There are three useful ways to look at this equation. So first of all, you can interpret it as just the classical harmonic oscillator with periodic forcing of the stiffness coefficient, right? So harmonic oscillator plus some perturbation. Second, well, just another physical interpretation. So this is nothing but the Schrödinger equation for cosine potential, modeling some particle in a one-dimensional crystal. And third interpretation we obtain under a change of variables. So here again we have a Schrödinger type equation, but with a rational potential. And so what is perhaps important to note here is that if we drop from this equation this term or this term, so this becomes equivalent to Bessel. Okay, so this Mathieu equation is in a sense a minimal non-trivial deformation of the Bessel equation. Okay. So now let us first consider Mathieu equation from this classical mechanics point of view. So let us pick some values for the frequency of our harmonic oscillator for this forcing term, and then picking initial conditions at random, we can have two types of behavior of our solution. So depending on the values of these two parameters, our solution will either blow up, so it is unstable, unless you tune your initial conditions in a very fine way, or it will remain bounded, okay, stable. So this is example for these parameters, which are rather close. And so in general, you have this kind of phase diagram in the plane of frequency and coupling Q, where these gray shaded regions correspond to equations with stable solutions, and white regions correspond to unstable solutions. So these two pictures that I had on the previous slide, they are located basically, so the solution which blows up is located somewhere here, and the solution which looks like periodic, but it is actually not periodic, it is somewhere here. Okay, and so what one is interested in, so one of the problems that one can ask, and which was studied starting from the beginning of the 20th century, is how can we describe this stability chart analytically? So how can we determine these functions a n of q, b n of q, which are called Mathieu characteristic eigenvalues?
Did people study the continuation of this picture of complex
I think no. Well, of course, I mean, you can are you asking about analytic continuation in omega nq, or?
Because normally, when you have such kind of picture, if you go to complex plane, it becomes kind of a Riemann surface.
Yeah. Okay. So in some sense, yes, there are some partial results, but it still remains on very rudimentary level, I would say. Yes. So this is what I will come to later on. Yeah. Exactly. Yeah. And yeah, so now if we want to interpret Mathieu equation as this Schrödinger equation for a particle in a cosine potential, then this, of course, corresponds to energy bands and gaps.
It's probably a very naive question. So, is your problem related to an operator which is self-adjoint, and do you have boundary conditions?
So in my case, it will not be self-adjoint, even though in this case, when I take this omega and q real, then the corresponding Hamiltonian is self-adjoint, I think.
So you are discussing some eigenvalues that could be in the residuum spectrum of the algorithm. It's not self-adjoint. You're not guaranteed, right, that these are generalized eigenvalues.
I actually cannot comment on this. So later on, the analogs of these eigenvalues, they will be definitely complex. So no self-adjoint operators. So this will be related to this inverse monodromy problem for my linear differential equations.
So your answer, how does it depend on the boundary condition that you assign to your problem? Just asking. If you want to define your operator as self-adjoint, I don't know, it's a second order differential operator, so it depends on some boundary condition to make it maybe a Stoney-Liouville problem.
It is not. So I will discuss what kind of functions are in the domain of this operator just in a moment. Yeah. Okay. So we can interpret this stability requirement in terms of monodromy of solutions of our linear differential equation. So because translating time by pi, we necessarily have a linear combination of solutions on the right with some matrix M in SL2R. And then, if... Yeah. So here I'm talking about real valued solutions, right? And so when the trace of this matrix is less than 2, this corresponds to the stable region. This is unstable region. And these curves that determine the endpoints of bands and gaps, they correspond to trace of the monodromy matrix equal to plus or minus 2. And in this case, so if you are thinking about the eigenvalues, so they are equal to plus 1 or minus 1. And so in this case, this Mathieu equation has exactly one periodic solution, and the other one is not periodic. Okay, so now how can one do the computation of monodromy? So we consider this Hamiltonian that we had. Yes, question? Yeah. So this is two-particle Toda. This Hamiltonian commutes with translations, as I just said before. And so by Floquet theorem, the joint eigenfunctions of H and translation operator, they have this form where this exponent mu, in principle, it can be arbitrary complex number if we allow this the energy and the coupling to be complex. And this Floquet exponent is related to monodromy matrix by this simple relation. So now, if we just take this Floquet solution and plug it in into the differential equation, we end up with a simple linear difference equation for these coefficients, and the existence of non-trivial solution to this equation is equivalent to requiring the vanishing of the so-called Hill's determinant of this infinite three-diagonal matrix. So here, this is basically just this relation, right? And the denominator, they are added just to make the determinant well-defined. Now, what is remarkable is that one can show that this determinant with for an arbitrary Fouquet exponent can be written in this form. So this guy is independent on monodromy. So the only place where the monodromy appears is this sign squared. And this means that when you have your differential equation, right, you have the energy, which is omega squared, and the coupling. So you can compute the monodromy by this formula, right? So you have no monodromy inside here. So this basically solves the direct monodromy problem for Mathieu equation, and because there is no.
No, but it's Q. It's just full. Not.
So Q is
here.
Q is here, but not on the right hand side.
Just from the determinant is it
Obvious.
obvious? These above diagonal and below diagonal lines are proportional to Q, yeah, and on diagonal then you have units.
Yeah.
Which is not Q dependent.
Well, because
some regularization.
It's the way how we wrote our difference equation from the very beginning. So, look, for example, this line here is just so these Q's are these Q's over here, and this nu squared minus omega squared is this guy over here. Okay, so basically.
Perhaps a relation like the sum of unities, yeah, from minus plus infinity equals to 0.
I'm not sure what you have in mind. Maybe I can say that for more.
You have to use some regularization, yeah, and probably in some natural regularization that disappears.
Well, the problem actually comes not from Q, but rather from this 2 squared, which grows when you go up in the diagonal. So this is why you have to divide by something. So this is the regularization. Yeah.
No, there's a question. So there's a question. So there's a quantization condition for the energy as a function of Coulomb domain.
Yes, in a sense, yes, exactly. So, but once again, I would like to stress that, so given the differential equation, we can compute this Fouquet exponent nu just from this equation, provided that we can compute this infinite determinant. And here it is actually not important to have, for example, Q small. So Q can be anything, and the determinant is still well defined. And under minimal adjustments, this procedure works for an arbitrary reasonable periodic potential. So this is not related to integrability or whatever.
Yes, it's an equation relating nu and Q.
So nu is a function of Q and omega.
Yes.
It depends.
It depends on Q. Yeah.
Of course, it depends. Yes.
Depends on this determinant, which is sort of not computed.
Well, it doesn't seem there is a closed formula, but. Now we can ask the inverse question. So suppose that we now want to compute not nu in terms of the energy and Q, but the energy as a function of monodromy and Q. And this was also done like in 19th century So there is the procedure using continued fractions. So for example, this equation here determines this series for Mathieu eigenvalue for generic Fouquet monodromy exponent nu. And so this is valid for Q small enough. So this has to be a convergent series, but the radius of convergence of the series is unknown. It is definitely finite, but depending on nu, but it is unknown. And so what we also have to note is that the coefficients of this function, which I will call accessory parameter function for Mathieu equation, so they have poles at integer non-zero values of this Fouquet monodromy exponent. Okay, so now comes the relation to quasi-classical Virasoro conformal blocks. So if we introduce instead of the energy, so this integrated version f, which is calligraphic f, which is a function of variable t and sigma. So then there is a conjecture which, once again, so for Hoyne equation, it is due to Zamolodchikov in 1986. Then for confluent versions of Hoyne equation, including Mathieu, I guess we have to call it probably Matone relation. So on the gauge theory side, the analog of this statement is in Nekrasov-Shatashvili, for example. Okay, and so so this once again, so the this accessory parameter function is related to quasi-classical Virasoro irregular conformal block, and so these poles in nu, they are related to this well-known poles of the coefficients of our conformal block. Right, and so yes, well, after quasi-classical limit, of course. So you are sending, yeah. So you are sending C to infinity, all conformal dimensions to infinity in such a way that some combination of this remains constant, and so this is basically what you get. So, for example, this 1/4, it comes from the central charge, basically. Right. So now, as I told you, so this accessory parameter function is computed for generic non-integer nu. When nu is equal to 0, we actually have no problem. And in particular, so this lowest Mathieu eigenvalue, so this function a0 of q, is related to quasi-classical conformal block with sigma equal to 0. Okay, so the rescaled conformal dimension equal to 1/4. And so now we would like to understand what happens in the resonant case when mu is non-zero integer. And in this case, on the differential equation side, there exists a similar recursive procedure which uses continued fractions and which computes the small q expansions of these eigenvalues. So these eigenvalues, they correspond to solutions of different parities. And the expansions have a different form comparing to, for example, this. So instead of expansion in q squared, the corresponding eigenvalues are expansions in q, so basically in square root of t. So this, on the conformal field theory side. So this is just the to illustrate the form of this expansion, a snapshot of DLMF. So you see that, for example, here for A1 of Q, so this is not a series in Q squared like we had before, but you have all powers of Q which are present here. Maybe later I will come back to this slide if I have time. Yes, they are related by changing the sign of Q. So basically this is the other branch of the square root.
Ah, okay.
Yeah. But on the other hand, if you look at A2 and B2, so these are not related. So this is like a general fact. And if you compare this these expansions, say, with the stability chart, then so you see that, for example, B1 and A1, they agree for a small q up to a constant term. Then A2 and B2 up to a linear term, this up to quadratic term, and so on. So the structure continues. And well, here you have coincidence up to exponentially small terms in Q. Okay. So people have studied the convergence of these expansions for Mathieu eigenvalues. So in the complex Q plane, this AN and BN, they develop branch points which correspond to double eigenvalues. So here we have a picture from a paper of these people, which like shows some of the branch points. So this is the Q plane. So this point over here corresponds to the value of Q, where A0 of Q coincides with A2, for example. Then this is the point where A1 of Q coincides with A3, and so on. And so in this way, you can have some kind of intuitive picture of the structure of analytic continuations of this function. So if you take, for example, A0 of Q, so there is some radius of convergence of this of the corresponding series. Then here you have a branch point, and then when you try to continue to another Riemann sheet, so you see, for example, this singularity where A2 of Q coincides with A4 of Q, and so on. So you actually have an infinite number of branch points on infinite number of sheets of the corresponding Riemann surface. And this is the analytic structure of the corresponding quasi-classical conformal block with this dimension. Okay, and one can even speculate about what happens for generic monodromy exponent here. So basically, what one has to do is to reflect this picture in the Q plane to the bottom, and then we can imagine that, for example, this branch point, when we switch on this new parameter or sigma parameter, it will move, and the counterpart of the bottom will move to the other direction. So basically, this corresponds to this double branch points where conformal block with sigma here coincides with conformal block with sigma plus 1 or sigma minus 1. Okay, so in this way we have some picture of analytic continuation of the quasi-classical conformal blocks, which is perhaps somewhat counterintuitive for at least some of you, because like if you take the usual conformal blocks, So these have infinite radius of convergence in the entire Q plane, whereas in this case, the structure is much more complicated. Okay, so what will be our next goal? So we will try to reconstruct this Mathieu characteristic eigenvalues from two particular logarithmic solutions of this Painlevé 3 equation. So now let me recall some basics on this. Painlevé 3 equation, or type D8 equation, is equivalent to this radial St. Gordon, which appears in these applications. And it can be put to this canonical form by a certain change of variables. And like accessory parameter function in Mathieu, so this Painlevé function Q solves the inverse monodromy problem, but not for scalar differential equation, but rather for 2x2 linear system. So this 2x2 linear system is here. So you can kind of recognize the same structure as in Mathieu. So this term would correspond to regular singularity. And then you have this irregular contributions which are required to be non-diagonalizable. And so this is this P, Q, and T. This is just a parametrization of the general linear system with this property. So now we have the following problem. So we want to find this P and Q, which corresponds to some prescribed monodromy data for this linear system. So I'm not going to talk about the details of how these monodromy data are defined. So this involves some Stokes matrices and connection matrices. What is important to know is that so this space of monodromy data is two-dimensional, and this means that basically we can change the one of the parameters, say t, and adapt the values of P and Q in such a way that this monodromy remains constant. And this leads to this isomonodromy deformation equations, which are equivalent to Painlevé 3 that I have shown you before. Now, these functions P and Q, they can be simply expressed in terms of a more convenient object, which is so this tau function, defined by this logarithmic derivative. So, for example, the function Q is some second order logarithmic derivative of tau. Okay, and yeah. So now, once we have this picture, let us discuss briefly the relation between Painlevé 3 and Mathieu. And this is actually a very elementary exercise. So, of course, when we have a 2x2 linear system, we can transform it into a scalar second-order differential equation for an element of the fundamental matrix. And so if we just try to figure out what this differential equation is, well, we end up with this kind of potential. So what is important to notice here is that in the initial linear system, we had only singularities at z equal to 0 and z equal infinity, right? But now, because of this gauge transformation that we have to use over here, we have this A to 1 element which appears in the denominators. And so the corresponding scalar differential equation will have not only the initial singularities of our linear system, but it will also have these false apparent singularities coming from A to 1. Which are over here. And so now we would like to reduce this Schrödinger equation to Mathieu. So the first part looks like nice. So this is what we would like to have. And this is the part that we would like to get rid of. And so how can we get rid of this? Well, there are two options. So first, we can send Q to infinity. So this corresponds to movable, so-called movable poles of Painlevé function Q of t. Or we can send Q to zeros in such a way that this guy can be somehow absorbed by these terms. Right. And so, indeed, so if we take our Painlevé 3 equation and take a movable zero at some point t equal to s, then just by some local analysis that we can understand that the behavior of Q function at this point is this. So we have a second order double zero. And then we have this free parameter E, which appears here. And the rest of the series you can reconstruct iteratively by using your differential equation. And if you compute the rest of the terms which appear in this expression for the potential, then, we can see that in the vicinity of this movable zero, our potential is precisely the Mathieu potential plus smaller terms. So if we are sitting exactly in the movable zero of Painlevé 3 function Q of t, then our linear system reduces to Mathieu. The position of this movable zero becomes Mathieu Complete constant. So this is what I denoted. So this corresponds to Q squared from before, or maybe Q squared over 16 or something like this. And the accessory parameters, the energy, it corresponds to the logarithmic derivative of the tau function. So this is, well, very classical. As I said, for Hoyne equation, it was already known in the beginning of 20th century. For Mathieu, I think it was Novak Shonov who did it in the beginning of 80s. But, I mean, this is quite straightforward. Okay, one more thing that I have to add here is that Painlevé 3 has Backlund transformations, which are in this case trivial. So this is just Z2. So in the language of radial Side-Gordon equation, this corresponds to just sending phi to minus phi. So this is kind of obvious. Now, in terms of Q, this is this transformation. And in terms of the tau function, well, the Backlund transformation has this form over here. So to every zero of the Q function, in every zero of the Q function, the associated tau function is non-vanishing, but this Backlund transformed one, tau twiddle, has a simple zero. And Backlund transformed solution Q twiddle has a second order pole. Okay, so we have this kind of duality which will be useful. Okay, so now let me summarize a little bit. So we have studied the problem of reconstruction of Mathieu equation from its monodromy, which was solved by inverting this Hill determinant expression with continued fraction. And the same reconstruction problem for linear system is equivalent to solving Painlevé equations, and the solutions is known for generic monodromy. Generic means, once again, so the analog of nu should be non-integer. And in this case, one has this solution. One has two kinds of explicit representation. One is Fredholm determinant, And the second one is combinatorial series, which is basically well, the Nekrasov instant and sums in the self-dual case. Now, yes, so this is what is said in the third point. So this is the theorem, right? So the tau function is given by this Fourier transform of the corresponding C equal to 1 conformal block. So this should be Z, sorry. Given by sum over pairs of partitions and so on. Well, I think so. This is all familiar for this audience. Okay, so the parameters which appear in the expression for the tau function, so this sigma parameter and eta parameters, they are related to monodromy. In particular, this so the sigma is more or less this Floquet exponent that we had before. Now, the small t expansion, small coupling expansion of this object is absolutely convergent in the entire complex plane in this non-resonant case. And so this is just a few first terms written explicitly. Okay, so now I come to describing the relation that we have over here, right? So the relation between Mathieu and Painlevé 3 functions. So as I told you before, so we have a reduction of the linear system to Mathieu equation when our solution Q of t has a double zero. Now this double zero corresponds to simple zero of the Backlund transformed tau function tau twiddle. So we have this equation over here. And then, so if we write this expansion, this equation using the previous conformal block representation of the tau function, then it reduces to this simple formula. What I haven't told you yet is that this conjugate monodromy parameter eta, it is actually also related to quasi-classical conformal blocks. But now, instead of differentiating with respect to coupling constant, we have to differentiate with respect to monodromy. And this is basically related to the fact that, well, sigma and eta, as well as the energy and coupling, they are kind of Darboux coordinates on the monodromy manifold, which is the same for Mathieu and for Painlevé 3 equation. So we have, in this way, a relation between
So there you substituted eta with the df in the sigma.
Yes, yes, up to some coefficients, yeah. And so we have a non-trivial relation between two kinds of special functions, right? So this is something that you can compute from Painlevé, from the differential equation, for example. This is something that you can compute from Mathieu, or in terms of conformal blocks. So you have one series corresponding to this, another series corresponding to this, and we have a relation between these two series, which actually allows you to reconstruct one function if you, or the series for one function if you know the other.
But this equation is equation for what? Just when you solve the equation, find the function.
This is. It depends on what you want or on what you know. So for now, this is just an identity between two kinds of functions. If you like to compute, for example, z, so then you can use this equation in order to compute f, and vice versa. Okay, but what I'm saying is that this type of equations, they allow to determine one function in terms of the other.
This false arbitrary S to sigma. S and sigma free variables.
Yeah. So this guy and this guy, they are basically formal series in S with coefficients which are rational functions of sigma. And well, yes, so this is an identity between the two series for arbitrary sigma. Yes?
Should I think about sigma and the F in the sigma as the WKB quantum periods?
Yes. So this is actually a WKB type of object, but you see in what I have tried to explain you before, you see that there is no need in WKB in order to compute this F on the differential equation side. Moreover, in this case, so the series for F is actually a convergent series, which is usually not the case for this resummed WKB periods. But otherwise, indeed, yes. So this.
So if I think on the dependence on H bar, for example, would sigma only have the 1/H bar and then the other period? So what is the normalization for this? Or do they both have all powers of H bar?
So I think that you have to include H bar into so sigma scale somehow with H bar, but S as well. So this means that, for example, if you think of this as a like conformal block series, so you will have a rational function of sigma as a coefficient. So this rational function, you will have to actually expand in powers of H in order to construct the results. So the corresponding WKB period, it will have no like poles in the coefficients of different powers of H. Does it answer? More
There are many H bars here.
Yeah.
One H bar is this H bar of quantum mechanics, another H bar is H bar of four-dimensional theory.
Right.
They're totally different.
But the H bar of the Mathieu would be the H bar of the Nekrasov theory.
No.
It's
But in the equation, like B, so the ratio
Yeah.
So the ratio person is not H bar of it's background parameters there.
The ratio of epsilon is the H bar of Nekrasov theory because once you send it to zero, you send it to zero direction.
Yeah, but that's H bar of quantum mechanics, yes.
Yeah.
But not of gauge theory.
Yeah, but I was saying that Mathieu should.
I see. Okay. No, that I can come.
Okay, so anyhow, there is a second blow-up equation which one can write, solving the connection problem for the non-Backlund transform tau function between the fixed singularity and the movable pole of Painlevé function Q of t. So this is another kind of identity, non-homogeneous one. And as I told you before, these blow-up equations allow one to reconstruct z for c equal to 1 in terms of f at c equal to infinity and vice versa. And so now the problem is about what happens when we have resonant monodromy. So when we have resonant monodromy, so let me just write a few terms just to give you an idea of what is going on. So let us write a few terms in the expansion of the tau, this Fourier expansion of the tau function. So we are interested in what happens, for example, when this sigma goes to 0. And So let us try to compare the coefficients of different powers of t, right? So we have a second order pole in sigma in here. And you see, naively, when we just take, for example, this guy and this guy, send sigma to 0, we have a second order pole here as well, and here as well. And this would exactly compensate the pole that you had over here if simultaneously with sigma you send to 0 the parameter eta, but in such a way that the ratio of the two remains constant. If you look more carefully at this equation, you can see that not only like the second order pole cancels, but also the first order pole contribution when you expand here will cancel. And what remains is only some finite expression, but this expression, because you have to expand in sigma, right, up to second order, so this will involve logarithms of t, well, squares and linear terms in logarithms of t. And, well, somewhat surprisingly, miraculously, this structure repeats when you go to higher order terms, so you can just turn Mathematica and check that when you do this kind of limit, then the corresponding tau function has this type of expansion. So it is a sum of well, integer powers of t, and here you have polynomials in omega, where omega is the logarithm of t plus some arbitrary constant, which now encodes initial conditions, one parameter family of initial conditions. And if you play with this, so you can compute these polynomials, you can produce a conjecture about the degrees, well, I have discussed the case sigma equal to 0, but the same type of manipulation one can do with sigma which tends to 1/2, which is this two one-parameter families of solutions of P3 that I was talking at the beginning. So this one-parameter families which we were missing in this general two-parameter solution. I don't know what would that mean. So this is a convergent series actually. So
yes. Normally the logarithms of t appear like degeneracy. So imagine you have two solutions which differ in some powers of parameters.
Yeah.
And then they degenerate and then give you logarithm.
Yeah. Of course. I mean, the appearance of logarithm is not like a surprise. For example, like if you have Bessel equation, right? For non-integer exponent, you have I nu and I minus nu, which are linearly independent solution. But
the question is, what is the second solution? So if sigma were arbitrary, if have expansion powers of t, then my question is, for this log t to appear, somehow you put contribution of different solutions so that they generate at some point.
But this is not linear equation. I'm not sure.
Imagine naive. So, as example, we said we have just two Bessel functions different by the values of mu minus one. You have linear combination with some mu and denominator, goes to limit and goes to 0, give you logarithm. But you have kind of combination of two different solutions which compete.
Right, but this then should be compared not with Painlevé functions, but with the solutions of the corresponding linear system, and this is indeed the case. It's like indeed you have two competing solutions, and you have to take something like difference of the two divided by sigma, and this is what corresponds to the corresponding to the relevant solution of P3. But P3 is non-linear system associated to the linear problem.
Is kappa related to the ratio to sigma?
Yes, it's basically.
You have two parameters, yeah, and then you have some kind of
Yes.
two-dimensional one.
Yes, exactly.
Yeah,
and it's actually a theorem that all Painlevé 3 solutions can be divided into so the moduli space of the solution consists of three pieces. So a two-dimensional piece which is described by this Fourier formula, and then you have one-dimensional pieces which correspond to this sigma equal to 0 and sigma equal to 1/2. Well, as we see, yes, but it's for now it's just a technical experimental observation. But now comes a theorem. So actually, one can. There is a technology for proving this combinatorial series representation for Painlevé tau function, which I probably not have time to discuss. This is related to this Widom determinant formula, the stuff like this. So you can actually construct a Fredholm determinant representation for the corresponding tau function, even if the monodromy is not semi-simple. So this is basically the corresponding Fredholm determinant. And so if you so in the semi-simple case, the expansion of this Fredholm determinant would produce unique-Russell functions. But in this non-semi-simple case, so you see these matrices B, PQ, CPQ, which appear in here. They are no longer Cauchy determinants. So it was the Cauchy determinants which led to unique-Russell functions. So here they are given by some more complicated but explicit expressions. So H, P, HQ are harmonic numbers. So this is something like the sum of 1 over k from 1 for k from 1 to n. And but still, I mean, you can, even though you cannot have the formula which is as explicit as in this semi-simple case, still, well, you can compute this the corresponding minors and get this expansion for the tau function. So basically, we have proved. Just a moment, 1/2 of this conjecture that we had on the previous slide. So we have proved the statement about this tau sigma equal to 0 tau function.
What's the principal difference between sigma equal to 0 and sigma equal to 1/2?
Well, in technical terms, so in this Fredholm determinant, you have building blocks which correspond to elementary parametrices that you use to approximate the solution of the corresponding linear problem. And so precisely this comes back to your question a few minutes before. So in the semi-simple case, these parametrices were made of Bessel functions like I nu and I minus nu. And in the non-semi-simple case, these parametrices are built of I0 and K0, so to say. But otherwise, this is actually more or less the same calculation up to some inessential technical complications. Okay, so in the remaining couple of minutes, so just how can we go back to Mathieu from this? So remember that Mathieu equation, it corresponds to zeros of Painlevé tau functions. So now, if you consider, for example, this Backlund transform tau function, say that it is equal to 0, and we now consider this as an equation for omega, which contains inside the logarithm of t, but also the monodromy parameter. So we can see that this equation admits an infinite number of solutions which basically differ by their asymptotic behavior as t goes to 0. Okay? And now, how do you compute the Mathieu accessory parameter? So recall that you just have to compute the logarithmic derivative of the non-transformed tau function at this point where tau twiddle is equal to 0. So you compute omega from this equation, you plug it into this equation here, and you recover all of the eigenvalues corresponding to this resonant monodromy exponents. So the general pattern is like this. So the equation for the tau function with sigma equal to 1/2 produces two solutions which I denote here, omega to NA, omega to NB, and the corresponding accessory parameters give A2k and B2k of Q. And likewise, the equation tau corresponding to sigma equal to 0, so the vanishing gives you once again two solutions, and the corresponding Mathieu eigenvalues are A 2k plus 1 and B 2k plus 1 of Q. So to summarize, so what we have seen in this talk. So first of all, this missing one parameter logarithmic solutions of Painlevé 3 admit both Fredholm determinant and combinatorial series representations. So this covers all of the solutions. And this infinite number of Mathieu characteristic eigenvalues can be actually repackaged into the conditions of vanishing of just two this pathological logarithmic Painlevé 3 tau functions with sigma equal to 0 and sigma equal to 1/2. So this is somehow completes the picture that at least like this part of the picture for non-generic monodromy. Okay. Okay, so the combinatorial series is this. So if you expand this guy in principal minors, so you will still have a double sum over partitions and single sum over integers, because, well, this different choices of principal minors will be labeled by these pairs of Maya diagrams with zero total charge. Okay, so the combinatorial structure of the series will be the same. The only difference is that when you want to compute the corresponding minors built of matrix elements of these matrices, so they are not Cauchy determinants like in some simple case. They are now more complicated. So you cannot have like a nice, well, at least I have not found.
Can you write it or
in terms of determinant of some finite matrix which has these elements.
If you want to have something similar to instanton partition function, you should not have it, because this is the point, naively, the point with non-local from field theory point of view. You have both A and AD going to 0, so you have massless both electric and magnetic states. So there is no room for any kind of Nekrasov derivation. Yeah, but maybe from that point of view you can recover.
That's why I'm asking.
Yeah, it's another similar like this analogs of these blow-up equations. If you consider the expansion at infinity, yeah, you have some formulas there which you can recover from equations that Pasha we're trying to look for, but there is no interpretation in terms of any instantonic sums because there are no instants.
Okay, so anyhow, I think this is the point where I should stop. So thank you very much for your attention.
Sorry, could you repeat what is H in that intermediate form?
Here, okay. So H is HK is sum for n equal to 1 to k of 1 over k, something like this. So if you want some difference of the gamma functions.
Question. So you mentioned this relation to Figol determinant, etc. I know that both Figol determinant and Painlevé 3 appeared for this trace-evident distribution, particular matrix ensembles.
Mm-hmm.
And my question is, one, you have representation in terms of the semi-infinite matrices. But could you say what kind of integral operator corresponds to those matrices? So could you just write in form of the Figol determinant, not of the matrices of the operators? How does the operator look like? Maybe I explain you better. So if I start from some integral operator, basically this is how the trace medium is here. We start from some integral operator, some kernel from the area functions, and they have shown that Figol determinant of these integral operators satisfies Painlevé 3 equation. But then you could, if you choose particular basis of function, you always represent integral operator by semi-infinite matrices.
Mm-hmm.
My question is, once you have semi-infinite matrix like that, I should be able to go back to intersect underlying integral operator which has this particular representation.
Well, if you want some kind of trace-evident like determinant, I don't know how to get it. So you do have a continuous, so you can represent this as a continuous Fredholm determinant, but you will not have, so your integral operator will not act on functions on some interval, it will rather act on functions on a unit circle.
Okay.
Yeah, so this, yeah, indeed. So you have such Fredholm determinant representation, and this is precisely where this I0 and K0 will appear.
And those operators, are they integrable?
Yeah. They are integrable. The only peculiarity is that they will not be scalar. They will be like 2 by 2. Mm-hmm. But otherwise, yes. Uh-huh.
Please.
So at some point you showed the blowout equation, and they involved some function z that was defined by three series of tau function with certain choice of coordinates,
Mm-hmm.
sigma, that were very important in the talk. But as you know very well, there's other expansions of the tau function if you renormalize it by some coefficient related to long distance versus short
Mm-hmm.
distance, and elementary free.
Yeah.
So is there a generalization of the blowout equations for the other choice of coordinates, so the Fogg-Gonchar type?
For Fogg-Gonchar, I don't know, but for this long distance, yes. Yeah. Or they are literally Fogg-Gonchar? Okay. So then, okay.
So let's think of again tonight's talk.